Gaussian random numbers are also very important. Many random patterns that we encounter are well described by a Gaussian. Because of this, the Gaussian is also known as the normal distribution. One of the reasons for the pervasiveness of the normal distribution is the central limit theorem. This theorem says that if we add up many independent random variables of comparable size and finite variance, the resulting sum is a random variable whose distribution approaches a Gaussian. To describe normal random numbers of parameters mu and sigma, we will use the PDF, to which we will refer as norm PDF, or simply phi of x, and then depending parametrically on mu and sigma, is equal to 1 over the square root of 2 pi sigma squared times the exponential of minus x minus mu squared over 2 sigma squared. Alternatively, we'll use the CDF, norm CDF, or capital phi of x, mu and sigma, which is defined in terms of the PDF as the integral of the PDF between minus infinity and x. Finally, the inverse of the CDF will be called norm inv, and we'll denote it as capital phi inverse, and it's a function of p, a probability, mu and sigma. Since p is a probability, will be between 0 and 1. To generate a random number from a normal 0-1 distribution, we'll use the function rand n, normal random. Let's go to the graph and try to understand what the parameters mu and sigma mean. Mu, in this case, is going to be the center of the distribution. It can be thought of as the mean, and that would be just the expected value of the random variable, or as the mode, and in this case that would be just the maximum of the PDF, and also as the median. The median means that the probability that the random variable has a value lower than mu is going to be equal to a half. That's the definition of the median. Finally, let's try to understand the meaning of sigma. Sigma is simply a scale factor, so it appears here as a scale. It can be thought of as the width of this distribution. So this parameter here would be proportional to sigma. This is the demo for the built-in function rand_n. Rand_n is used to generate random numbers from a normal 0-1 distribution. To do this, we just type rand_n at the command line, press intro, and we get a sample from a normal 0-1 distribution. To generate a new independent sample, we can type rand_n again, and we get a different value. It is also possible to generate a matrix with m rows and n columns from a normal 0-1 distribution using the command rand_n mn. Here is the sample. We get 3 rows and 5 columns of normal 0-1 independent random numbers. Let's illustrate how the histogram of a sample of normal 0-1 random numbers traces the bell shape of the Gaussian distribution. These values are being sampled from a normal 0-1 distribution. Once again, we're using the height of the bars to indicate how many samples fall in a particular region. Once all the values in the sample have been generated, the vertical bars form what is known as the sample histogram. The profile of the histogram should approximately follow the profile of the PDF, in this case, the bell shape of the Gaussian distribution. Again, the histogram and the PDF are not exactly equal because of sampling fluctuations.